In this video, we're going to prove a number of facts about triangular numbers. The first one, number 4, in front of us, says prove that the square of any odd multiple of 3. Well, here's an odd number, and I'm multiplying it by 3. If n is an integer, which it is, 2n is even, you add 1, it's odd. That's an odd multiple of 3. I square it, and they tell me that this is the difference of two triangular numbers. And they even tell us the triangular numbers. So this is what we want to show. Well, t sub n, 9n plus 4 is 9n plus 4 times 1 more all over 2 minus this, which is 3n plus 1 times 1 more all over 2. Question is, does that equals this? Well, everything's over 2. If I distribute this, I'll get 81n squared plus 81n plus 20 minus, when I square this, I'll get 9n squared plus 9n plus 2. Everything's over 2. 81n squared minus 9n squared is 72n squared. 81n minus positive 9n is 72n. And 20 minus 2 is 18. If we do this division, we get 36n squared plus 36n plus 18. Plus 9, excuse me. 18 over 2, 9. Now, I factor out a 9. 9 times 4 is 36. So it's 9 times 4n squared. 9 times 4 is 36 times n gives me that. And 9 times 1 gives me that. Well, the 3 is 3 squared, and this is 2n plus 1 squared. We have a rule at a to the m times b to the m. You can multiply the bases first and then raise it to the mth power, as long as those powers are the same. So we have 3 times 2n plus 1, all to the second power. But if you look, that's exactly what we're supposed to get. An odd multiple of 3 all squared. Okay. Number 5 has their few parts. In the sequence of triangular numbers, find the following. Two triangular numbers whose sum and difference are also triangular numbers. Well, t1 is 1, t2 is 3, t3 is 6, t4 is 10, t5 is 15, t6 is 21, t7 is 28, and t8 is 36, and t9 is 45. Well, if you look at t6 plus t5, that's 21 plus 15, which is 36, which is t8. And t6 minus t5 is 21 minus 15, which is 6, and that happens to be t3. So I found the two triangular numbers whose sum in, I found a pair of two triangular numbers whose sum and difference are both triangular numbers. One should suspect there's going to be more of those. Okay, letter B. 3 consecutive triangular numbers whose product is a perfect square. Okay, so Tn times Tn plus 1 times Tn plus 2. This is supposed to be a perfect square. Well, Tn is that number times 1 more over 2 times T sub n plus 1, which is that number times 1 more over 2 times T sub n plus 2, which is n plus 2 times 1 more over 2. Well, I would jump on the squares. That product is n plus 1 squared, and that product is something squared. It's n plus 2 squared. So I'm not going to touch that. And what survived is n times n plus 3 over 2 times 2 times 2, which is 8. Now, we want this to be a perfect square. Well, one necessary condition is that 8 goes into either n or n plus 3. So let's see what the possible numbers of n are. Well, we could have multiples of 8, 8, 16, 24, 32, 40, and this can also be multiples of 8 when x is 5, when n is 5, or 8 more, 13, and 8 more, and 8 more, and 8 more. Because if n plus 3 is 5, and you add 8, then n plus 11 is 13. And we get a multiple of 8. If n is 13, n plus 3 is 16. Okay, so let's try this. Now, just for completeness, this is n plus 1 times n plus 2 all squared. I need for this to be a square. Well, if n is equal to 5, I get 5 times 3 more over 8. That's 5, no. If n is 8, I get 8 times 3 more over 8. That's 11. If n is 13, I get 13 times 3 more over 8. That goes in 2 times, that's 26. If n is 16, I get n times 3 more over 8. Excuse me. 8 goes into 16 2 times, and I get 38. That's not working. So these are done. Let's try 21. You get n times 3 more over 8. That goes in 3 times, get 63. Almost. Let's try n is equal to 24. So you get n times 3 more over 8. Well, 8 goes in here 3 times. 3 times 27 is 81, which is a number squared. Just let n be 24. So you'll have 24, n is 24, times 27 over 8. 8 goes in here 3 times, and you'll have n plus 1 times n plus 2, all squared, times 3 times 27, which is 9 squared. So you have 9 times n plus 1 times n plus 2, all squared. And this is an integer. So n is 24. We didn't have to do any of that. We found n was 24, so n is 24. So it'll be t24 times t25 times t26, and that's going to be an integer squared. If you really want to see that is true, t25 times t26 times t27, that's t25 is 25 times 1 more over 2, t26 is 26 times 27 over 2, t27 is 27 times 28 over 2. That's 26 squared. That's 27 squared times 25 times 28. 25 times 28 over 4. Now it's time for me to go because that's not working. Oh, excuse me. I hope this helps, but 2 times 2 times 2 is 8. Okay, my biggest mistake was I'm supposed to start with T24, sorry. T24, no T27. So T24 is 24 times 25 over 2. T25 is 25 times 26 over 2. And T26 is 26 times 27 over 2. I definitely have 25 squared times 26 squared. But what's left over is 24 times 27 over 8. Well, that's 3. So you have 25 squared times 26 squared times 3 times 27 is 81. That is known as 9 squared. So this here is 25 times 26 times 9 all squared. And you want to multiply that out, fine. But I showed that when you multiply those three numbers, you do get something squared. And that's all I was asked to do. Now, they want the same thing where the sum of 3 successive triangular numbers whose sum is a perfect square. So now we have Tn plus Tn plus 1 plus Tn plus 2. Well, Tn is that number times 1 more over 2. And just so I don't forget, that's supposed to be something squared. Plus that number times the next number over 2. Plus that number times the next number over 2. Now, for example, this one has n, but this one doesn't, so I can't factor out n. This one has n plus 1. Oh, good, this one has it. But oh, that one doesn't. So there is nothing common. I'll multiply those. I'll get n squared plus n. I'll multiply those plus. I'll get n squared plus 3n plus 2. Multiply these. You get n squared plus 5n plus 6. And if you add these, everything's over 2. You get n squared plus n squared plus n squared, known as 3n squared, plus n plus 3n. Plus 3n is 4n, plus 5 more n is 9n. And you have 2 plus 6, which is 8. Now, we want this to be a perfect square. It has to be, the numerator has to be 2 times a perfect square. Because if the numerator was 2 times some number squared, when you divide it by that 2, you'll get m squared, or a perfect square. So we just try. If n is 1, you get 3 plus 9 plus 8, which is 20. Half of that is 10. That's not a perfect square. N is 2. 2 squared is 4 times 3. 9 times 2 plus 8. This is 28. Half of it is not a perfect square. N is 3. 3 times 9 is 27. Plus another 27. Plus 8. This is 54 plus 8. 54 is 62. And half of that is 31. Well, the numbers are going higher. I'm hoping the next one will be 36. 3 times 4 squared is 3 times 16, which is 48, plus 36 plus 8, 48, 38, and 6, 70, 80, 92, I guess. And half of that is 46. No such luck. And is 5. 5 squared times 3 is 3 times 25 plus 45 plus 8. That's 110. 128. Ooh, 128. Half of that is a perfect square. So let n be 5. T5 plus T6 plus T7. T5 plus T6 plus T7, well, that is 8 squared. Just suffer through it. It works. Okay. If the chart number 6, if the triangular number Tn is a perfect square, so Tn is n times n plus 1 over 2, this is a perfect square. Then they're saying that T sub 4n times n plus 1 is also a square. So if this is true, then what's below is true. Well, T sub any number is that number times that number plus 1 all over 2. Well, if you multiply that, if you distribute that, you're going to get 4 squared, n plus 1 squared, plus, now you multiply all of this times 1, and you get 4n times n plus 1 over 2. Well, what you can factor out from here is 4n times n plus 1. When you factor the 4 out, you'll have another factor of 4 left. You factored out n, so you have another factor of n. You factored out n plus 1, so you have another factor of n plus 1 plus, well, we have one of those, plus 1, all over 2. First thing I'll observe is 4 goes into 2 goes into 4 2 times. So we have 2n times n plus 1 in front, and here we have 4n squared plus 4n plus the 1. Plus the 1. Well, this is 2n times n plus 1, and this here is 2n plus 1 squared. And this is not something squared. Oh, okay. So now we know n times n plus 1 over 2 is m squared. Okay, so you know what? I'm going to keep this as 4. and then I have to divide by 2. But I'm going to do this very cleverly. This is 4 times n plus 1 over 2 times 2n plus 1 squared. Well, 4 is 2 squared. By assumption, that's m squared times 2n plus 1 squared. This is 2 times m times 2n plus 1 all squared. And 2 times an integer times an odd number is an integer. Let me say it a little better. 2 times an integer times an odd integer is an integer squared. So we just proved that one. Okay, I don't think I want to do part B. Use part A to find 3 examples of squares that are triangular numbers. Okay, let me just quickly try that. T1 is 1, T2 is 3, T3 is 6, T4 is 10, T5 is 15, T6 is 21, T7 is 28, T8 is 36, which is 6 squared. So we know that. But we know if Tn is a square, then T sub 4n times n plus 1 is something squared. So 8. 4 times 8 is 32 times 9 is 288. So 288 is something squared. I don't know what it is. Okay, but now I know this is something squared. So I know that 228 is a squared. Well, that implies T sub 288 times 4. 32, 8, 11, 9. And then you multiply this by 229, and whatever you get, 912 times 229 is a perfect square. Now you can take that number for n, and T sub 4 times that number times one more than that number, plus 1, 229. So here's one number, here is 2 numbers, and here are 3 triangular numbers that are perfect squares. Once you find 1, take that number, multiply it by 4, and then multiply it by 1 more than 4, and you will have another triangular number. I know that's true. We just proved it. Number 7. Show that the difference between 2 consecutive triangular numbers is always a cube. 2 consecutive. So Tn plus 1 minus T sub n. That's the difference between the squares of 2 consecutive triangular numbers. Well, the first number is n plus 1 times n plus 2 over 2 all squared, so it's over 4, minus n times n plus 1, square that, over 2 squared. Everything's over 4. I can factor out n plus 1 squared. And then I get this minus that. I get n plus 2 squared minus n squared. So we have n plus 1 squared times something else over 4. Now remember, whenever you have a squared minus b squared, whatever being squared, you can add them in one bracket and you can subtract them. When I add those, I get 2n plus 2. And when I subtract these, I just get 2. And everything's coming together perfectly. We have n plus 1 squared. From this factor, I can pull out a 2 when I get n plus 1 times another 2 all over 4. Well, 2 times 2 over 4 disappears. So we have n plus 1 squared times another copy of n plus 1. This is n plus 1 cubed. So it really is true. If you subtract the square of 2 consecutive numbers, you will get a cube. For example, t1 is 1, t2 is 2, 3, t3 is 6. If I do t cubed squared minus t2 squared, t3 is 6. Get 6 squared minus 3 squared. Well, I can add the numbers being squared. I can subtract the numbers being squared. I get 9 times 3, which is 27, which is 3 cubed. Or I could have said 9 is 3 squared times another 9 is 3 cubed. That's probably better. Let's not go to 27, because knowing 27 is 3 cubed is a lot harder than knowing that 9 is 3 squared. Okay, that completes this video on some facts about triangular numbers. If you like math like this where we prove things, please subscribe to my channel. Leave a comment, good or bad. I love reading negative comments. If you have a if you have a theorem that you'd like for me to prove, and I know how to prove it, even if I don't know how to prove it, leave it in the comment section. And if in fact I do know how to prove it, I will post that video. Most of all, watch and learn.